Hello, my name is Riley Delker, and today I will be giving a presentation on forward and inverse kinematics as it pertains to a robotic frog. The paper I will be covering is titled Forward and Inverse Kinematics of a Robotic Frog, written by Anish Desari and N.S. Reddy. Topics covered will include a thorough analysis of a frog's jump, how the robotic frog biomimics a real frog, how forward and inverse kinematics are used to simulate a jump, and how artificial neural networks help in improving said jump. Here we can observe how a frog jumps in slow motion. Frogs and other creatures exhibit a pause and leap type of locomotion where a long pause precedes a large jump. This type of locomotion is extremely energy efficient and versatile since the jump covers a large vertical and horizontal distance while the pause allows adequate time to recharge and assess the next jump. The jump consists of 3 stages. The foreleg flex, where the front legs initiate the jump. The leg extension, where the hind legs push off the ground. And finally, the hip swing, where the hind legs move to the most extended position. All of these movements occur within milliseconds of each other and require extreme precision to execute correctly. Notice how the frog's body maintains a steady arc through the air, and how the frog's rear feet stay in contact with the ground for as long as possible. These 2 factors are crucial for executing a balanced jump, and will be recreated in the robot using forward and inverse kinematics. In order to understand the robotic frog's design, we must first understand the anatomy of a frog's jumping mechanism, the leg. The leg of a frog is mainly built up of 3 links: the femur, the tibia, and the tibiale. However, a 4th link exists. This link is the hidden body link. This link is important because it connects the center of mass of the frog to the leg, and is crucial to maintain balance during locomotion. So in total, there are 4 links: the foot, shank, thigh, and body, and 3 joints: the ankle, knee, and hip. Now that we understand how a frog jumps, we are ready to analyze the robotic frog. Pictured here is the robotic frog. It consists of a main housing unit that stores the electronics, 2 jumping legs with 3 revolute joints that are powered by servo motors, and a ratchet and tendon system that initiates the jump. It is important to note that the forelegs are entirely passive and do not contribute to the jump in any way, and that all the legs exist in the same plane. By superimposing the anatomy of a frog over the diagram of the robot, we can see that both legs are similar in design. However, there is one problem. Since the robotic forelegs are passive, the jump is initiated by sliding the housing unit forward on linear rails using a spring-loaded ratchet and spool system. Suddenly pushing the robot's center of mass forward generates sufficient forward momentum to initiate the jump. This is important because when the center of mass moves, the length of the body link changes. This greatly affects the forward kinematics of the model. Pictured here is a simplified model of the robot and its joint angles and its home configurations. Before carrying out any calculations, some assumptions must be made. The main body and forelegs are condensed into one end effector, the center of mass, and all the leg links exist in the same plane. And since the foot will remain in contact with the ground for as long as possible, phi is 180 degrees. By splitting up link 4 into its x and y components, we eliminate the issue of link 4 changing length. However, by doing so, 2 extra links and 1 prismatic joint are added to the model. Now we are ready for forward kinematics. Forward kinematics is defined as the computation of a robot's end effector as a function of its joint angles. Here are the parameters that engineers use to define the coordinate frames of each link, resulting in coordinate frames that look like this. The end effector position calculation is simply a compilation of how each coordinate frame rotates around each z and x axis, and how far each coordinate frame is translated across each z and x axis. Since every leg link exists in the same plane, we can use simple trigonometry to relate each coordinate frame to each other via this transformation matrix. Of course, the only important end effector is the center of mass. Table 2 shows how each coordinate frame relates to one another in space. These values are a robot's DH parameters and are used in transformation matrices and kinematics. This transformation matrix is only useful for one successive pair of coordinate frames. By multiplying the transformation matrix with the end effector's original point in space, the end effector's new point in space can be determined. This process can be repeated an infinite number of times by multiplying each link's transformation matrix together. Since the end effector on link 5 needs to follow a predetermined path, one transformation matrix is made by multiplying each link's transformation matrix with each other. By combining equations 2 and 3 together, equation 4 is made. This equation is used to find the end effector's final position relative to its original position as the legs move. Unfortunately, the robotic frog doesn't have time for that many calculations. Since each joint needs to adjust in a fraction of a second and the end effector needs to follow a very precise predetermined path, forward kinematics is not very feasible. This is where inverse kinematics come in. Inverse kinematics is very similar to forward kinematics, except that it solves for the motions necessary to achieve a desired position, instead of solving for individual joint angles. This process is much more quick and accurate than forward kinematics. Looking at how a frog jumps again, we can see just how precisely the legs move, and how the body follows a near-perfect arc. Inverse kinematics is much more practical for this kind of operation. The engineers chose to use the method of Jacobian for the calculations. A Jacobian is a linear approximation of a matrix of partial derivatives. Each partial derivative is a combination of components of vectors, the vectors being the links, and the components being how each coordinate frame rests in the x, y, and z axis as pictured here. E is the Jacobian for the robot frog's center of mass. Only the foot, shank, and thigh links, and the ankle, knee, and hip joints affect the world position of the end effector. Since the leg exists in the x and y axis, there is no need for the third term, which would be the z axis. Simple trigonometry is used to find the coordinates of the end effector as a function of link lengths and joint angles, as pictured in equation 7. By taking the partial derivative of equation 7 with respect to each joint angle as they relate to the x and y axis, the final Jacobian matrix is derived. The next step is carrying these equations into the real world. This is accomplished with equation 9, where delta E is the change in end effector position in space, J is the Jacobian of the center of mass, and delta theta is the change in each joint angle. Multiplying each side of the equation by J inverse, the change in joint angles is isolated. However, J inverse rarely exists, so a pseudo J inverse is substituted in using singular value decomposition. Singular value decomposition reduces a matrix to its constituent parts to make subsequent matrix calculations easier. Now that the joint angles can be solved for, the robotic frog can practice its jumping. Pictured here are the results of the Jacobian method of inverse kinematics. As you can see, this method is extremely accurate. The frog center of mass follows the predetermined path perfectly without needing to include any body link calculations. This method is a little too perfect, though. Mechanical limitations prohibit certain joint angles from being achieved, and the servo motors aren't quick enough to execute such precise movements in such a short amount of time. Some compromises must be made. This is where artificial neural networks come in. The artificial neural network, or ANN for short, can solve for joint angles with pre-programmed parameters such as impossible configurations and timing constraints. In addition, The ANN can learn from itself through multiple simulations in order to find the most efficient and effective path. The ANN consists of three layers. The input layer, which is the end effector coordinates. The processing layer, which takes the end effector coordinates and computes the joint angles necessary to achieve the next set of end effector coordinates. And the output layer, which is the newly calculated joint angles. These new joint angles result in new end effector coordinates, which then feed into the processing layer to begin the cycle anew. In the end, the ANN is trying to match the end effector with a predetermined path as closely as possible. It is programmed to move each joint angle a maximum of 5 degrees at a time without violating any joint limitations, and can be improved by adding or taking away neurons in the second layer. The robot was then simulated multiple times with this strategy. The results of these simulations are pictured here. The engineers chose to simulate the jump with neuron amounts ranging from 20 to 55 in 5 neuron increments. It should be noted how the percent errors reach a minimum at 40 neurons. This is because if too many neurons are added, they begin to overcompensate with the joint angles. If the joint angles could be changed by less than 5 degrees at a time, more neurons could result in a more accurate end effector path, but at the cost of a timely jump. This may affect the overall performance of the robot. In the end, more experimentation is needed. Overall, the science behind the jumping frog is much more complex than springs and joints. A coordinated jump requires complex movement, balance, and even thought to execute perfectly. Forward kinematics can be used to achieve movement, but is ultimately unreliable in applications such as this. Fluid movement and control is needed for a precise jump, which is why inverse kinematics and artificial neural networks are used in tandem to execute an accurate jump. Inverse kinematics uses precise calculations that can simulate organic movement by using the end effector's coordinates to solve for possible joint angles instead of using joint angles to find the end effector coordinates. But inverse kinematics is only useful when there is a brain to coordinate it, which is why the ANN is crucial to the performance of the robot. By tweaking how the robotic frog thinks and calculates its jumps with varying neuron amounts and joint movements, the performance of the jump can be improved with little error. Thank you.